Alright, so if you remember from the past video that we converted, the very first one that we converted our values there into the frequency domain. And now to express a wave in the frequency domain, you have this. Now let's put it as S. Remember that your S is equal to JW. So E of S, your wave equation for in frequency domain will be E, using Euler's theorem, E naught, that's your amplitude, E raised to the power minus propagation constant, and in the direction of propagation ours was Z, then plus epsilon this E raised to the power this. Alright, now this part is in case it is propagating in the negative Z direction. So every negative Z gives you a minus propagation constant Z. So it's for negative Z's, negative Z axes. But since we're not moving in negative Z axes, this would come down to 0. We're only moving in one place at a time. So this would come down to 0 because we're going in our positive Z axis. Alright, so that means all we have left is this in our frequency domain to be this E raised to the power minus this. Now we need to convert this back into our time domain. So to do that, E of t is going to be the real part of this. So we find the real part, that's RE E. Now we add, it's a conversion process. I'm not so sure of whose rule this is, but it's more or less a conversion process. So you add EJT, EWJT to it. More of remember your Fourier transform back into time domain is going to be integral of minus infinity to infinity of the function times EJWT. Yes, so this is trying to convert it back to t. So if we do that, we have in the t in the time domain is equal to the real part of E. Now I'll remember that our propagation constant is equal to alpha plus J beta, and we already know the equation for alpha and J beta. We can easily find them. This is E naught E raised to the power minus alpha Z minus J beta Z, then dot E JWT, right? And then our ET is going to be RE, that's the real of, now let's take the J's together, so that'll be E naught E raised to the power minus alpha Z dot E J into bracket WT minus BZ. And then if we take the real side means real side is always R cos theta. Our real is always R cos theta. So out of, remember that EJ theta is equal to R into bracket, R EJ theta is equal to R into bracket cos theta plus J sine theta. So if we're to only consider the real, hence we kept on putting RE, the real is now going to be R cos theta alone. So all we have left, so this would be our R. This will serve as our R, while this will serve, this angle here will serve as our theta. So therefore we have, for the general wave, E, the general wave in the time domain, is going to be E naught E raised to the power minus alpha Z cos WT minus beta Z. And that is the equation wave equation for your electric field. Now for your magnetic side, you have something similar. It's going to be H naught this time, e raised to the power minus alpha z cos wt minus beta z. But your H naught is equal to your epsilon over your Z naught. Now your Z naught is your characteristic impedance. It's your characteristic impedance, and it is given by Z naught is equal to the square root of this all over 1 plus connectivity over WE squared is power 1 over 4. And it's more that it's a complex value, so it can be denoted as the magnitude of this times the angle, or the magnitude using the Euler's equation, e raised to the power j theta. So this is your characteristic impedance. This is your field. This is the wave equation for the field. So this is the final equation. These are the final equations for waves. And that's how we can define it in this curve. So from this very diagram that we drew, you'd see that there's a sine wave. This is your E going this way. And then your B field going this way. So as you can see, that forms your electromagnetic wave. See, going up in the y-axis, going in the x-axis, and going y-x. So your magnetic field is on one axis, while your electric field is on the other axis. Alright, we've actually solved a whole lot. Wow. Now explaining your graph. Remember that in free space, let's consider the 3 times. Free space, then alpha is equal to 0, beta is equal to our propagation constant, magnitude of our propagation constant. So if alpha is equal to 0, then our E naught alpha, E naught e raised to the power alpha z would be just E naught. So E naught e raised to the power minus alpha z, which is going to be E naught e raised to the power 0, and that's going to be E naught. So you see that the amplitude will not reduce, it stays constant, so there's no attenuation. And B is going to be our propagation constant in that direction, z. So our final waveform for free space would look like this. ET is going to be E naught cos WT minus this x. But this is equal to W squared, this epsilon, so we can just put it inside. But this is our equation for free space. Now for a lossy dielectric, For a lossy dielectric, it means your conductivity is barely equal to 0, so alpha has a value, beta has a value, and it's going to be very, very complex. It's better you find the value using the formula for B and A, for beta and alpha, and then put it back into your wave equation. So generally, this is your wave equation. Your equation for wave. This is it. And this is what you'd use throughout. Next up, finally close with pointing and the power.